Okay, in this module, I'd like to talk about shear strength design. For shear, we don't check the serviceability level, but only at the ultimate limit state level. Shear behavior is very complicated, so I'd like to talk about the mechanism of a shear cracking, and it's a behavior up to the ultimate limit state. And I'd like to then move on to the ACI 318 code equations. Even though it's a couple of equations, it's very tough to calculate by hand because of several reasons. And I propose the modified ACI 318 equations for simplicity. So I like to focus on the modified ACI 318 equations in this module. Shear strength design. Shear strength design of a prestressed one-way members. Here we have a rectangular sectional, simply supported beam without reinforcement under 2-point loads. And it's an elastic beam. Because it shows the linear stress distribution and second order parabolic distribution for shear stress. So it's a before cracking if it's a concrete. And point A, which is a little below the neutral axis depths, principal tensile stress is obtained. So under bending, you have a certain stress, tension, and then shear stress is almost maximum, V. Then in the Mohr circle, that point is right there, F minus V. And the other point in the Mohr circle is 0, V. And you just try to draw the Mohr circle. Principal tensile stress can be calculated, and that's from the center of the circle plus the radius of the circle. Okay? And when it reaches to the strength, say Ft star, it will crack. With 0 F at the bottom, 0 shear stress at the bottom, you will have a maximum F. Then that F is automatically equal to principal tensile stress. You don't need to rotate any point. It's just located at the x-axis. So then crack is vertical. If it's at the CGC level, you have a maximum shear stress, but then F is 0. Then you got to rotate the point to the principal tensile stress with a 90 degree in the Mohr circle. Then on the beam is a 45 degree angle. So it's a 45 degree angle. So cracks like this. Starting from the flexure crack, and it develops to web cracks. And its shape is a C. And that is a compression zone strut. So principal tensile stress is higher if you have a tensile axial stress. With no tensile stress, F0, then your circle will be smaller. So then principal tensile stress is small. So you got to have a large F, which is axial stress. So shear cracking will initiate at the tension side following the C trajectory, And when it reaches to the tensile strength of concrete, Ft star, so when this equal to Ft star, you will have a forced shear cracking. And this equation can be expressed like this. It's just same equation, okay? So in terms of a V, you can express that with a small f and small ft star. And you will see that if you have axial compression minus value, then you will find out that, oh, shear capacity will increase. Okay? Because V right now is the shear stress at the onset of a cracking. Okay? So with that minus F value, you have a beneficial effect of a prestressing. And in the Mohr circle, it shows like this. So if you have an axial precompression, your Mohr circle is shifting more like a left-hand side of a y-axis, and principal tensile stress is very close to the 0 point. Okay, you know, V positive or negative, it doesn't really matter. It depends on the sign convention definition. You know, I'm talking about the value of Ft right there. And it's far from the Ft star. So to make sure this touches that criteria, you gotta have a much larger V so that shear capacity is increased. And also this angle's theta is getting smaller. And it also helps that if it's cracking is not 45 degree, but more like a little bit flat, then it is intercepted by more number of stirrups, if you have stirrups in that beam. So it also helps. Pre-compression is beneficial. Flat cracking is also advantageous. So shear capacity of a prestressed concrete beam is larger than non-prestressed reinforced concrete beam. With that philosophy, ACI 318 equation is developed. And first, you see that the web shear capacity. Okay, how can this equation be interpreted? Well, web cracking capacity, stress capacity is defined like this. This is from the previous equation. And say tendon is flat, so the VP is assumed to be 0. Okay. And we got to look into the first two terms. So in this equation, we plug 4 square root to FC prime right there, which is a tensile strength from the direct tensile test. Modulus of rupture, you know, in PSI unit, 7.5 square root FC prime as a modulus of rupture. But direct tension test is going to be much smaller, so that 4 times square root FC prime. Even to be more conservative, 3.5 is used right there. And then this is also simplified to this equation. And here F is negative value. So in the code, every notations are defined as positive. So later, Precompressive stress is input as a positive value, so the minus value is changed. Because with the negative value, it's going to be added. So with that positive absolute value, it should be plus. So that's the final equation. And then you just multiply by the cross-sectional area using the effective depths of up to that pre-stressing steel from the top. And it should not be smaller than 0.8 H. Okay? Alternatively, ACL allows you to check using 4 square root FC prime instead of a 3.5 if you check that principal tensile stress. How about the incline flexure cracking? The equation in the code looks like this. Well, VD term and FD term here is considered because during the laboratory test, they developed the equation, they mean, previous researchers, using the applied loading, and then it's a point load, so then A to D ratio is same as the V to M ratio, and so VI and M max is defined as factored forces, like a shear force or moment under externally applied load, like an actuator load. So it didn't include the self-weight, so later they added the self-weight contribution right there. In the code, it's defined as a shear force due to unfactored dead load. So it may be interpreted as self-weight plus superimposed dead load. However, when you look into the literature, you will find out that actually it's a self-weight. So it's a little different from the definition in the code. And cracking moment here means you have a forced flexure cracking at the bottom. So this equation is familiar to you. And FPE here it's not the steel effective stress. It's a compressive concrete stress due to pre-stress at the level of a CGS. So it's a concrete stress, okay? And with the 7.5 square root FC prime, basically it's the same as the way of calculating the cracking moment. So MCR with 7.5 square root FC prime, but here it's a little conservative. MCRE with the 6 square root FC prime. So second term is the additional shear necessary to initiate incline cracking in addition to flexure cracking. And total VCI lower bound is 1.7 square root FC prime BWDP in PSI unit. Shear strength design procedure is indicated. First, you calculate the factor shear force for that section, and phi here is the strength reduction factor of 0.75 typically. And required VS is calculated to be VU over phi minus VC. VC, you can get this from approximate method or detailed method, which is the smaller of a VCI and VCW. And Vs provided is a V FYT D over S, same as the RCs. S is the spacing of a shear reinforcement. A V is the cross-sectional area of the shear reinforcement per layer. So required Vs was Vu over phi minus Vc. So instead of a Vs, you plug right there. And then phi is moved to denominator, numerator, and also in front of a VC. So once you assume your AV, you can determine your your S, depending on the demand, the shear demand, and the concrete capacity. Or you can determine your spacing of a shear reinforcement first, and then figure out AV. Either way is fine. Also, you check that maximum spacing should be smaller than 3/4 of a total depth, or 24 inches. If your required VS is greater than 4 square root FC prime BWD, then your maximum spacing is reduced to half. If the required VS is greater than 8 square root FC prime BWD, which is a very large demand, then you gotta enlarge the section. If VU, which is the factor of shear force, is in between phi, VC, and then half of that, then you gotta provide the shear reinforcement anyway for minimum, AV minimum. Okay. Now I'd like to introduce the proposed modification of ACI 318 equations. And details are provided in the reference, which is published in Concrete International. Okay, VCI equation was like this. You have a DP, which is the effective depth to prestressing steel, and D is the overall effective depth for both prestressing and non-prestressed reinforcement. Both should be at least 80% of total depth. Here you have many terms that requires excessive computational time. And unlike the reinforced concrete new shear equation, shear strength equation, it does not capture the effect of longitudinal reinforcement ratio. So that proposal is like this. Self-weight contribution is very small when we check that using the existing database. If we check the effect of self-weight on these equations, it's smaller than 5%. So VD is eliminated, FD is eliminated, and then VD is eliminated. Okay. And also, we just use a factor shear and factored moment instead of a VI and Mmax only for the externally applied loads. And that way we consider the self-weight. And MCRE is also modified to MCR, which is more familiar to us. And also, K factor is introduced. That is 4 times raw WT to the 1/3 power. Raw WD is calculated like this. Okay, D, by the way, this is not defined by any code. But people believe that this is calculated like this. The steel reinforcement yield stress and pre-stressing steel yield stress is used with that effective depth for each respectively, and D should not be less than 80% of H. So that way, longitudinal reinforcement ratio effect is addressed. So here, you see that the effect of a longitudinal reinforcement amount on the shear capacity, clearly there's a relation. Because you see that the green parts are much higher than the blue parts or red triangulars. So modified equation looks like this. VCI is equal to 0.6 lambda. Lambda is live aggregate factor. K is 4 times raw WT to the 1/3 power square root FC prime in PSI unit BW dP plus VU MCR over MU. MCR here, you don't have a small FD term, and then you use 7.5. Lower bound of a VCI is same as a RC. Similar to RC, except that K factor. So with the modification in comparison with the existing database, its impact on the calculated shear strengths to test measure shear strengths ratio would be minimal. How about Web-Shear Strength, VCW? This is the current equation, and points to be modified include unexplained jumping shear capacity in partially prestressed concrete members. With the very small pre-compression, shear strengths will be merging to 3.5 square FC prime BWDP. However, that's way greater than RC's 2 square root FC prime BWD capacity. So that's not explained well. Also, it does not capture the effect of longitudinal reinforcement ratio, and perhaps the relationship between VCW and FPC is not linear. So this graph shows the effect of a pre-stress on web shear strengths. Green dashed line is the line that shifted from black solid line by changing the constant in front of a square root FC prime from 3.5 to 2. That way, for the beams with relatively small pre-compression, shear capacity is more reasonably fitted. So 3.5 maybe not appropriate, even though it was a conservative derivation in the original literature. And how about the relationship between FPC and VCW? Well, in the previous derivation, it's from the principal tensile stress. However, empirically, it is more fitted. It is better fitted with that square root FPC. So the relationship between FPC and VCW is not linear, and also with the square root FPC, the constant should be changed like this. So that green line better represent the database. Also, there's a certain relationship between the reinforcing bar ratio to the capacity of a web shear strength capacity. So final modification is VCW is equal to 2 lambda K square root FC prime plus 12 square root FPC times BWDP plus VP. K is the same as before. And also you see that this modification improves actually a little bit than the original ACA 318-19 web shear strength equation. So for the detailed method, for both beams with and without stirrups, you have smaller standard deviation and a little bit lower the measured data to calculated data so that it's less conservative, but it's more accurate. For the beams without startup, it's slightly smaller than the ACA 318. And overall, the results are similar and original philosophy is preserved. Here's the approximate method. The current equation is just simple. It looks simple, but approximate method is supposed to be very simple. First, the condition that you can use for this approximate method is not clear where that comes from. And this lower bound and upper bound is so unclear to me. And D here it's hard to calculate. Anyway, it should be not less than 0.8 H, but it's not applicable to DP. DP could be less than 80% of H. So approximate method supposed to be simple. However, the current equation is not simple, so the purpose is to simplify this equation. So this is the modified equation. 0.6 lambda K, the longitudinal reinforcement effect, is multiplied. And the second term, instead of a VP, VD is introduced. You know, for that drape tandem profile, DP calculation is also not easy. Along the lengths, even it's not designed completely at the design phase. So DV here is more simplified. It's just 0.8 H or DP. For example, for pretension system, DP calculation is not too difficult because normal is a straight tandem profile. For post-tension with the drape tandem profile, you can take the 0.8 H. And also D outside the parenthesis is also simplified to be dV instead of a D. D, you gotta calculate the average effective depth for both prestressed and non-prestressed reinforcement, where the non-prestressed reinforcement has a profile. It's not easy. So dV. Anyway, D should be greater than 80% of H. Conservatively, we can take 80% of H. And also the condition that you can use for this approximate method is much simplified. And lower bound K factor is multiplied. And here upper bound is a little increased with that use of a dV. Okay? And here, when you calculate the K factor, rho WT here can be based on dV, because dV calculation is then very simple here. So that's the comparison with the database. The red colored points are not for this equation. These data are having FPC smaller than 525 psi. So only looking at the blue colored circles, it's conservative enough. Upper bound, lower bound, and in between those upper bound and lower bound. So here's the summary of a measured shear capacity to calculated shear capacity. For the beams with and without shear reinforcement, well, standard deviation is a little increased, and average is also a little increased. So it's not as good as the ACA 318 equation. However, it's very easy to use. So that's kind of the major advantage. And approximate method is to be conservative. So for the conservativeness aspect, it performs well, and it's not too bad. It's similar to ACI 318 equations. Shear strength design exercise. We have two examples. Both are from the PCA notes. In PCA notes, ACI 318 equations were used. And in this example, I use modified equations. First example, for the T-shaped pretension composite girder with the 2.5-inch thick slab topping, show the hand calculation procedure of a VC at the selected location at 8 feet from the end, and determine the shear reinforcement for the entire member. Single T precast member with V-shaped profile, so that DP from the precast top is 33 inches and 8 feet distance, it's a 26.4. Precast member, 5,000 psi specified concrete strength. It's a sand lightweight concrete. And topping is a 4,000 psi. Effective stress is 150 ksi. Tendon eccentricity is given. That's from the precast CGC. Span length 60 feet. Self-weight of a precast and topping concrete is indicated. Sectional properties of only precast section and total composite section are already calculated at 8 feet distance from the end. VUMU, internal force, shear force and moment at 8 feet distance for the factor loads are calculated, as well as the self-weight induced internal moment at that section. Let's check whether we can use approximate method. FPC should be calculated. Unlike the regular precast girder or post-tension member, because it's a composite section, CGC for the composite member should be found out, and before applying the slab topping, it was actually the precast member only. So FPC should be calculated carefully following the definition, and this is exactly same as that in the original PCA notes. Anyway, it's calculated to be 355 psi, way smaller than 525 psi. So approximate method cannot be used. So let's use the detailed method. First, Flexure-Shear Strength VCI. Okay, DP at that 8 feet distance from the end is 28.9 inches, smaller than 30.8. So both D and DP are taken as just 80% of H, 30.8. K factor is calculated. Here we don't have mild steel reinforcement, so calculation is a bit simple. So DP is exactly the same as a D in this example. Anyway, it's smaller than 1, so I take 1. FPE is the bottom compressive stress by the prestressing. It's a very simple equation. We all know this for the precast member, so it's just calculated like this. And cracking moment also, in this case, composite section. So I use the composite dimensional properties here. And 7.5 instead of a 6. Lambda is 0.85 because it's a sand lightweight concrete. So 1,000 is for the conversion. So M cracking moment is 679.3 kip fit. VCI is already calculated at that section. Pretty simple. Okay, so 80.69 kips. Lower bound is checked. Okay, VCI is already calculated. How about the VCW? Well, VP is the vertical component of a post-tensioning forces. So actually it's a V-shaped profile. So that slope is obvious and it's calculated like this. And then effective force was 275.4 kips. Because it's almost horizontal, almost flat. So vertical component is not that much, but it's non-zero. So 6.89 kips is added later here. And 2 times lambda 0.85 K is 1 square root of 5,000 PSI. So it's to get the kips unit. 12 times 355. It's already calculated in the previous checking of the approximate method, whether that can be used or not. And then DP was 80% of H only, so 92.21 kips. So we take the smaller of a VCI and VCW. VCI was smaller, 80.69, so that's the governing strengths. And strength reduction factor is 0.75, so 60.52 kips. And what was the demand? 44. So VS required is only 2.72. So it's very small amount of shear reinforcement is needed. But this is greater than 50% of a phi VC and small. Well, it's not smaller than phi VC, so slightly greater than that. Anyway, you compare with the AV minimum. That's 0.079 inch square per foot. So it's way greater than calculated. So we got to use 0.079 inch square per foot. In that region, 8 feet from the end. So you got to do this practice for the entire section. Also, this required VS is smaller than 4. Maximum spacing is 24 or 3/4 of H. So 24 is the maximum. With this amount, well, actually the calculated spacing will be very large. So I use the maximum spacing of 24 inches at that location. And by repeating this procedure for the entire length, of course, this takes time, and you may need to have a software or even spreadsheets. It can be calculated like this. So you have a factored shear demand, and I just express this with the only absolute value. And approximate method cannot be used, but just for your reference, it's plotted. And detailed method, well, it has a development length so that it's actually slope here, and then this is because of a VU over MU function. So you don't need that much of a shear reinforcement, but only for the small region. You use the shear reinforcement, and I use the minimum amount of a shear reinforcement and maximum spacing. Okay, only that region. And left-hand side, it's calculated using the current ACA 318 equation, detailed equation, and approximate equation, though it may not be applicable. So for the entire section, I use the 2 over number 3 bars and 18-inch spacing. 24 is a little large. So that's the final design. Second example, simply supported pretension ledger beam. So it's an inverted T-shape and calculation procedure of VC at selected location of 1.75 feet. So within the transfer length. So we got to calculate the effective stress at that location exactly. And it's a straight tandem profile with that eccentricity of 10 inches. And it's a one concrete, 6,000 psi, normal weight concrete. Total steel strand area is a 2.448 inch square. Effective pre-stress is 162 ksi. Span length is 24 feet. Self-weight, live load are given, and sectional properties as well. At 1.75 feet, I calculated VU, MU. By the way, I am not sure whether I need a self-weight because it's the only dead load here anyway. That's from the unit weight of the concrete. MU. So let's check whether we can use the approximate method. Transfer length is function of a diameter of the strand, and it's approximated as 50 times dB. So total transfer length of the half-inch diameter strand is 25 inches. And 1.75 feet location effective stress or force can be calculated. Stress is anyway 1.75 times 12 over 25 times 162 and multiplied by the cross-section area. So pre-stressing force at 1.75 feet is 333.12 kips. Pre-compression, in this case, it's just one section. It's a non-composite section, easily calculated. 578 psi, greater than 525. So you can use the approximate method. Approximate method, dV is simply taken as 80% of H, 28.8. K is calculated, but it's smaller than 1, so it's taken as a 1. Everything else is quite straightforward. The lambda is 1, K is 1, 6,000 psi concrete strength. VU is calculated, MU is calculated. dV is 28.8. Very easy. 321.77 kips. Lower bound, 53. Upper bound, 157.94. So one upper bound value, 157.94 kips governs. With the strength reduction factor, it's 118.46 kips. How about detail method? DP is 31 inches. So I just want to go with the DP and no bonded mild steel reinforcement in this example, so it's the same. D and DP is same. K, because we have a very small amount of rebars, 0, so it's smaller than 1, so it's a 1. FPE, compressive stress at the bottom, is calculated. Cracking moment is calculated, also very straightforward. So VCI at 1.7 feet location from the end. Nothing difficult. Okay, so it's 380.27. Lower bound is 57. Okay. How about the Web-Shear Strength? It's a straight tandem profile VP 0 and FPC is 578 psi. Okay, finally you get 164.95, which is smaller than VCI. So this would govern. So Web-Shear Strength will be the detailed method VC with the strength reduction factor is 123.71. In comparison with the approximate method, it's a little larger. So approximate method is typically more conservative, and 123.71. It's not too different actually. Okay, so I like to use a detail method. So here is a detail method, and then required the shear VS is 25.77 kips. Okay, and with this 12-inch spacing assumed, a V required is calculated to be 0.2217 inch square, and it's greater than the minimum AV. Okay. And also maximum spacing 24. And we repeat for the other section locations. Finally, I got this. Okay, since left-hand side ACA 318 method, and then right-hand side modified method. The red lines are approximate method, and green lines represent the detail method, and black line is the demand. So hashed area is the required shear reinforcement required area, and it's a similar between existing method and then proposed method. So for the N region, I like to use 2 of a number 4 bar with the 9 inches. So this is the capacity, and in the mid-span region, I use 2 lakhs of number 3 bars, and with the spacing of 9 inches. Anyway, it's smaller than maximum spacing, and it's greater than the demand. The required VS. And original design is like this in the PCA notes. And if I use the same one, it's the same. The blue line, you have a little bit smaller capacity than the original equation because we fit it with existing database, and we try to be accurate more. Approximate method is quite similar with a little bit lower strengths for the modified version. Okay, so I just wanted to go through the shear strength calculation and the entire design for shear and shear reinforcement using the modified version of ACA 318.